In these slides, we want to give a definition of what a capacitor is. So a capacitor, if you have two conductors and they are separated by some distance, they're not connected to each other, and one conductor has a charge Q and the other one has a charge minus Q, this combination of two conductors with these properties is called a capacitor. So as you can imagine, since you have plus charge here, and of course any extra charge goes to the surface of the conductor, and here you have negative charge, and the negative charge goes to the surface of the conductor, there's some electric field that's going from the positive conductor to the negative conductor. As long as there's an electric field in this region, then there's also a potential difference between the two conductors. So if you take the V2 to be the potential of the positively charged conductor, and the potential is the same at any point inside or on the surface of this conductor, as we've seen before in equilibrium, and V1 to be the potential of the negative conductor, and this V1 value, the value of the potential is the same anywhere inside or on the surface of this conductor, then there's going to be a difference in potential between these two conductors. And the difference in potential can be obtained from the electric field by doing this integration. So let's say you make an experiment and you put an amount of charge Q on this conductor and an amount of charge minus Q on this conductor, and let's say the value of Q is plotted here on this axis. So let's say you put an amount of charge Q on the conductor, and so you measure then the potential difference for this particular charge. You're going to get at one point. What happens if you increase the charge? So if you make the charge larger value, then of course the electric field is going to be stronger. And since the electric field is stronger, then the potential difference is stronger. So when you plot the potential difference for this particular charge, you're going to get another point on this line. And if you increase the charge even further, the electric field will increase even further. And since the electric field increases, the potential difference will increase, and you get another point on this line. Basically, no matter what kind of amount of charge you put on this combination of conductors, plus Q and minus Q, no matter what the value of Q is, always the charge is going to be proportional to the potential difference, and any point that you obtain will lie on this straight line. So the charge is proportional to the potential difference. This is something you can verify experimentally. And the constant of proportionality is what's called the capacitance of this this capacitor. So the charge Q is the magnitude of the charge on either conductor. It's a positive number. The potential difference is the potential on the plus conductor minus the potential on the minus conductor, so it's always a positive number also. So the capacitance itself is a positive number. So this is the capacitance also can be seen as the slope of this line then, because if you take the slope at the slope of the line, you get the charge over the potential difference. That's what the capacitance of the device of this capacitor is. It's basically the slope of this curve. There are two ways you can change the capacitance of this system of conductors. We're going to discuss this in detail during the chapter, but I'll just give the idea. One way, you can change the geometry of the conductors, and this involves either changing the shape or the distance between the conductors. The other way you can change the capacitance, which we'll take a bit later, is by inserting some insulating material between them. So the act of inserting this insulating material will change the capacitance of this device. So we're going to study this case in detail later, and we're going to study this case in detail also later. Since we have charge separated by some distance, then there's some energy stored in this system. And so capacitors actually act like a device that can store energy, electric energy. And we'll discuss this also later on, and we'll try to find a formula for the amount of energy stored in a capacitor. The units of capacitance are farads, so Q is in coulombs and delta V is volts, so a farad is 1 coulomb per volt.